next talk is on finding subgraphs with site constraints, and Ciaran is presenting.
I'm Ciaran McCreesh. This is joint work with Özgür and Chris Jefferson at St Andrews, Jess Enright and Patrick Prosser, who are with me at Glasgow, and Steffen Zschaler, who is at King's. And we're interested in subgraph finding, but with side constraints. So in a basic subgraph isomorphism problem, we're given a small graph, which we're calling the pattern, and a larger graph, which we call the target. And the idea is to find a copy of the pattern inside the target, or to show that it doesn't exist, or we might want to find all solutions. Now, in this particular case, we're dealing with directed graphs, and we also have labels on vertices. And the rule here is that square vertices have to be mapped to square vertices, circular vertices have to be mapped to circular vertices, and so on. And the numbers on vertices are just identifiers. They don't carry any other meaning. And we can model this in the essence modeling language as follows. We're going to set up a set of labels for vertices and a set of labels for edges. We're going to be given a number of pattern vertices and a number of target vertices. We describe a pattern graph as a partial function from a pair of vertices to an edge label, and similarly a target graph is a partial function from pairs of target vertices to an edge label. And then we describe pattern and target labels as total functions from a pattern of a target vertices to labels on vertices. This particular problem instance has 3 different label types and 1 edged label type. We have a 3-vertex pattern graph, which has an edge 1 to 2 of type 1 and an edge 2 to 3 of type 1. And then vertex 1 has type 1, vertex 2 has type 1, and vertex 3 has type 2. And similarly, we can describe the target graph. And then we're looking to find a mapping, so a function, which is total, so every vertex has to be mapped. And it needs to be injective, so we can't use the same vertex twice, from the pattern graph to the target graph, such that labels are respected, and such that for every edge with a label in the pattern graph, the corresponding edge with the correct label is present inside the target graph. And we can solve this, and we find there are two solutions to this particular instance. So we can go 1, 3, 4, or we can go 2, 3, 4, like that. Although sometimes when people talk about subgraph isomorphism, they actually mean an induced subgraph isomorphism. And in this case, you're not just looking for the edges to map up, you're looking for non-edges to map up as well. And this is also similarly easy to model in essence. And if we run this, we find now there is just one solution. So we can no longer find the solution that goes 1, 3, 4 because of this additional backwards edge that's present in the target graph. And it turns out in practice people want to solve all kinds of varieties of the subgraph isomorphism problem. One example is in temporal graphs. So in a temporal graph, edges have an associated timestamp, which in this case we're using as integers, and I'm showing them in blue in the graph. So this edge occurs at time 1, this edge occurs at time 2. And again, we can describe this very easily in essence. This is what an instance looks like. And we don't need to change the rule to find an exact temporal subisomorphism. We're just saying match the edge labels up exactly. And we find there are 2 solutions here. I have turned off pattern vertices for this example. So we have 2, 3, 1, and so we have times 1 and 2. And the other solution is 2, 3, 4, again with times 1 and 2. Sometimes though people want to solve a slightly different kind of problem. This is called an offset temporal subgraph isomorphism. And in this case what this pattern would mean is that we want to find this edge and this edge such that this edge occurs 1 unit of time after this edge. It doesn't matter when they are, as long as this number is 1 bigger than this number. And again we can model this very easily. We just have this additional O and then we have an offset on what we're searching for. And we run this and we find there is an additional solution now. We can go 1, 3, 5, and we see that we have 2 and 3 as our timestamps. That's okay because they are 1 apart. And finally, people are sometimes interested in finding what's called an order embedding. In this case, all we're saying here is that this edge has to occur sometime after this edge. And again, we can model this very easily. And what we find is yet another additional solution. So we use vertex 2, vertex 3, and vertex 5. And here we have timestamps 1 and 3, which respects the order that the timestamps 1 and 2 appear, even if it doesn't respect the exact values or an offset. Another kind of subgraph isomorphism problem that occurs in practice is on something called a typed graph. A typed graph is a special kind of graph where, in addition to vertex labels being an exact mapping, vertex labels carry some additional structure. So this is a possible type graph, not the only type graph for this pattern graph. The way you read this is that squares can have there can be edges between squares and squares, there can be edges between squares and circles, and between circles and squares. And if you look at where the edges occur in this pattern graph, this does respect this typing structure. The same in a target graph. A possible typing for this target graph is we can have edges between squares and squares, from squares to circles, and between squares and diamonds. The particular application we're interested in involves something called a retyping problem. So in this case, you don't have to map square to square, for example. You are allowed to map different shapes as long as you do it consistently, and so long as the shape mapping also defines a graph homomorphism, so also respects the structure of these type graphs. Just briefly, I'll go through how we model it. What we're now finding is both a relabeling function as well as a subgraph isomorphism. We go into more detail in this in the paper. Again, we can describe an instance and we can find the solutions. And one other type of problem that occurs commonly in the literature is a costed subgraph isomorphism problem, where we're somehow looking for the least expensive assignment using some arbitrary objective function. It shouldn't be surprising that this is very easy to model in CP. Unfortunately, this doesn't work so well in practice. I'm looking at a fairly challenging set of standard benchmark instances here. I'm plotting cumulative number of instances solved over time, comparing the essence plus minion constraint programming approach to the current state of the art, which is Glasgow subgraph solver. And reading across the graph, the dedicated solvers are 3 or more orders of magnitude faster than the straightforward constraint programming approach. And this isn't that the solvers do well on different kinds of instances. It is nearly always the case that using the dedicated subgraph solver is just flat out several orders of magnitude faster than a constraint programming approach. But the state-of-the-art, the Glasgow subgraph solver does not support side constraints. It does labels, it does directed edges, but pretty much nothing else. It is effectively a constraint programming solver for graph problems, but it uses special data structures and propagation algorithms, and it would be an awful lot of work to add in all the usual general purpose constraints into this solver. It would also be very difficult to add additional non-graph related variables into the solver. So what we're looking to do here is to get the performance of the Glasgow subgraph solver, but to use a general purpose constraint programming solver to handle side constraints and additional variables for us instead. So how do we do this? The solution we settled on is as follows. We let the external constraint programming solver have a model of everything except possibly the graph constraints. The Glasgow subgraph solver just gets the subgraph isomorphism part of the problem. We run the Glasgow subgraph solver, and it is allowed to feed partial assignments to an external constraint solver, and it can say either propagate this and tell me no, that's unsatisfiable, or as far as I know that's okay, and when you do this, list any deletions that you infer. And we can also say given a complete set of assignments to at least all the variables that the subgraph solver knows about, go and give me one or all solutions respecting this assignment to the entire problem. And we can make these solvers talk using a simple text protocol communicating over named pipes. We have implemented this in Minion for the constraint programming solver, but nothing we've done is particularly solver specific. From a high-level modeling perspective, the main challenge is that we need the two solvers to have a consistent view of what the graph variables are, and we need to recognize when we're dealing with a graph problem where we can use a subgraph isomorphism solver. This is done in the Essence toolchain just using pattern matching and through a simple text file explaining variable remapping to the Glasgow solver. But finally, we have to decide how often we talk to the external constraint programming solver. We could just use it as a solution checker. We could, for example, do root node propagation additionally. We could propagate at every node in the search tree inside the Glasgow subgraph solver, or we could do something cleverer, which is what we settled upon. Most of the application benchmark instances we have are ridiculously easy and don't allow us to differentiate between designs, so we designed some experiments to challenge the system instead. Firstly, using no side constraints, what we see is the Glasgow solver is much faster than the raw CP approach, but with hybrid modeling, solution checking is as fast as the native approach for longer runtimes once it catches up. The startup overheads are due to high-level modeling. These are very large graphs we're dealing with. And the propagating at every search node approach introduces quite a lot of overheads. We see it's over an order of magnitude slower than just doing solution checking. But again, propagating isn't really doing very much. The CP solver might infer a few things that the Glasgow subgraph solver didn't know, but probably not very much. And the rollback line is actually identical to checking. I'll explain what this means later on. Now let's actually put some side constraints in. We're going to say that any solution you find has to use more odd vertices than even vertices in the target graph. I implemented this by hand in the Glasgow subgraph solver. This is the Glasgow plus line. This was quite a lot of programming effort compared to my high-level approach, but it's there for comparison purposes. And here we see that solution checking again performs quite a lot better than propagating, but doing propagation doesn't pay off. And the rollback approach is the best of all, and again I'll explain what that approach is later. Now here's a different side constraint. We say we have to use less than 3 odd vertices. This is a different constraint because we expect this will actually propagate early on in the search tree, unlike previous constraints. And indeed we see in this case that propagating is much better than simply solution checking. And again the rollback approach is slightly better still. And finally we're going to say, okay, you've got to map odd vertices to odd vertices, even vertices to even vertices. In this case, propagating good, solution checking utterly appalling, and the rollback approach very nearly as good as implementing this by hand. So what is the rollback approach? Well, we propagate at the root node. This is probably always worth doing just because this might get you an awful lot of information very quickly. And then we don't talk to the CP solver again until we've found a solution. We ask the CP solver to check a candidate solution, and if it rejects it, we backtrack, and then we call the CP solver with full propagation enabled. If the CP solver still says, no, this is unsatisfiable, we backtrack again, do another full round of calling the CP solver for full propagation, and we keep backtracking until the CP solver is happy. It may give us some deletions, but it doesn't say this is obviously unsatisfiable. And once it's done this, we continue again without calling the CP solver to do any more propagating until we reach another candidate solution. And this is heavily inspired by backjumping and conflict analysis in SAT solvers and some of the things that SMT solvers do. But it doesn't require the CP solver to be able to produce conflict clauses, which is quite beneficial from what we're doing. And this seems to be the best approach we have so far. So for hard instances, what we're suggesting is great, it performs very well. It's also extremely useful for prototyping and rapid data exploration. The high-level modeling language does introduce very large startup overheads, which make this challenging for use in some applications, particularly if those that involve solving very large numbers of very easy problem instances very quickly. But this is down to the high-level modeling rather than using a CP solver per se. And as is so often the case, the key thing to getting all of this to work is to know when to do strong reasoning and when to give up and be stupid and fast. Thank you.
Peter is fast again. Yes, go ahead. Peter?
Sorry, I was actually doing the applause icon, but I will raise my hand as well.
Sorry,
so, because
I got confused. Okay.
Yeah, there seems to be no reason why you couldn't use a learning solver, and then you would get basically a back jump reason, right? And then you could do it much more directly.
In principle, yes. The main problem is finding a modeling language and a solver that doesn't mind if you give it a table constraint with 500,000 entries.
Okay.
That's not a problem.
In Chuff, the table constraint is mapped to clauses, so
yeah. So long as you don't do any pre-processing, for example, that's quadratic in the size of the table constraint, I suspect that that could be worth looking at. It'd be interesting to see whether we actually learn anything, because learning is surprisingly weak on these subgraph problems for ideas that we don't understand.
I think, but this is not about learning. This is just checking an answer. You're saying, oh, here's a conflict, and just minimizing the conflict, right?
Yeah.
So then you get a better back jump point, really. So it's much, much simpler. I know, as we have well experienced, learning for these graph problems is hard.
Yeah. Yeah, no, I'm planning to give that a try at some point.
What's the size of those graphs?
You
said it was large, but I didn't know what that meant.
Yeah, so the limits of what we can do currently are the target graph's about 10,000 vertices and arbitrary densities. Basically, so long as you can fit it in memory in an adjacency matrix, we can probably handle it.
Okay. Any other questions?
Can you add arbitrary side constraints? So really any kind of constraint I come up with, I can add it using essence and your approach.
If you can express it in CP, then yes.
Okay. Great.
Yep. You can add in variables. Anything you can express in CP, so long as you can model it, and so long as you can still represent the graph in such a way that it's obvious what the subgraph isomorphism problem bit of the problem is. Yeah, it's quite happy.
Okay, great, thanks.
Would you be able to use that special constraints in the first talk?
Possibly.
But I mean, maybe that's too hard a question.
It's more, yeah. So those constraints are more for graph generation and subgraph finding problems.
Right, but they were about symmetry breaking also.
But you can do this to put symmetry breaking in if you like. The Glasgow solver does actually do symmetry breaking natively, so you wouldn't need to. But yes, in general, you could use this as a way of eliminating symmetries in search if you wanted to.